as you get into expanding your network, one of the issues you'll run into with your switching architecture is looping. So for example, if you have a couple switches, and then those switches are interconnected. Let's say you're trying to do redundancy, which is a good idea on your distribution and core layers. If you're trying to do redundancy with Ethernet, you've just created a loop. So if we have a host off of one of these switches, and the host sends a broadcast packet, it's going to go out the links from the switch. That'll then get sent to each other switch, and so on, and vice versa. And it's going to get broadcast all over your network in a giant loop, because Ethernet does not have a TTL. So remember with IP, with IPv4 we have that time to live value, and IPv6 there's the hop count value. So every time a layer 3 packet makes it through a router, that value gets decremented, so that if it reaches 0 after 100 hops or whatever it is, it'll get dropped off the network. You don't have that with Ethernet. There's nothing in layer 2 for that to decrement in such a way as it passes through a switch. So if you have some sort of loop like this, and a device sends out say a broadcast packet or some other kind of packet that gets stuck in this loop, you'll just continuously use up bandwidth. You'll continuously use up processing power on your switches. It's a bad situation. So spanning tree has been developed to solve that, and there are other versions of similar protocols by other vendors that are not spanning tree, but what we teach here is spanning tree. What spanning tree does is help resolve this issue, and the way it does that is by electing a root. Electing a root bridge, which is a term for king of the switches, essentially. So if in our 3-switch environment here, we could theoretically say the top one would be the root. So that's king of the switches. The other members would not be root, so they would just be regular member switches. Spanning tree would then determine the proper way to get to that root switch, and then put one of these links into a blocking status in order to turn off one of these links, essentially. And then that would prevent a loop, because you would only have 2 out of those 3 links then. That's the general idea of spanning tree. And those links are kept up and live. They're just prevented from forwarding frames. So they're not put into a shutdown mode or anything like that. They're still kept up, but spanning tree puts them into a special blocking status. So what runs in spanning tree is the spanning tree algorithm, of course. And the way it runs is you enable spanning tree on all of your switches, and all the switches exchange their spanning tree bridge protocol data units, BPDUs. The root bridge is the one that's going to have the lowest bridge ID, and the backup root is the second lowest bridge ID. So the bridge ID in spanning tree, everything in spanning tree is based off of the lowest wins, opposite from OSPF and such, where everything the highest wins, everything in spanning tree the lowest wins. So the root bridge has the lowest bridge ID, which would be either the lowest priority level, if you configure a priority level, or it's going to be the lowest MAC. So this is also where having loopbacks come in handy, because you could have no priorities set, but then the one with the lowest MAC address on its loopback would then be the winner. It's common to also make your root bridge the core switches in your backbone. So potentially up here you'd have like a big chassis switch, and then that would be your root, and you would do so by giving it a very low priority level so that it would take over ownership of that root status. So the way spanning tree determines which links are good and which ones are bad, and who is the winner of that algorithm essentially, is all roads lead to root. Kind of like all roads lead to Rome. Everything points to root, and then it determines which links are non-important essentially, and the less impressive of the links, and then it will disable those. So what it'll do is it will calculate the cost of these links, similar to OSPF, where it will determine how fast each link is and determine what that cost is. So some of the costs you'll see are, for example, for 10 gigabits, the cost would be 2. 1 gigabit, the cost would be 4. And for 100 meg, our cost goes up quite a bit to 19. And then if you're unfortunately running 10 meg, your cost is 100. So it'll add up, if we had other switches here as well, it will add up the cost to get to root. So let's say we had additional connections here, and we had, I'll put down the cost values. So we'd have like a 10 gig, a 10 gig, we'll have a 4 for 1 gig, 19, and it'll add up which links are preferred based on the lowest cost. So it's pretty simple. So if you're from down here on this lower left switch, it's going to determine, well, is 2 plus 2, so that's 4 to get to root, is that lower than 2 plus 19 plus 4? Well, yeah. So this connection over here would be the better connection to use. So that's the basic idea behind spanning trees. It adds up that cost just like OSPF does. So the lowest wins. The ports, after it calculates what costs are best, it'll place these ports into the specific modes to accomplish preventing this loop. And those different modes are there's 3 different modes essentially for ports, and then one additional one. So what you have is a root port, you have a designated, and then you have an alternate / backup, and then of course we have disabled, which is different from blocking. So we'll get to that. So a root port points towards root. So after we determine who our root is based on that lowest ID, lowest MAC or lowest priority, all the other ports that point towards root are marked as root. So all roads lead to root. So for example, this would be a root port, this would probably be a root port, this would be root, these could be root, because they point upwards towards that root switch. This other link here, for example, is going to be either designated and alternate. So one of the side here is going to be designated, and one of the side is going to be alternate. Designated, let me write this down first for root. So root points to root essentially. Designated means that it's in forwarding status, but it's not root. So that's basically all non-root ports. And you'll notice on the root switch I didn't write any statuses yet. That's because root, since it is root, has no ports that point to root, So all of the ports on a root switch are in that designated status. So that's a designated port. This link here, it's going to base it off of that calculation. So it's going to add up that cost to get to root. It's going to say, alright, so 19 plus 2, is that less than 19 plus 4? Yes. So then this side, this switch would probably win and would say this is a designated port and this is the alternate port. The alternate port is in blocking mode. So alternate really means disabled, but still in up mode as far as configuration is concerned. Just Spanning Tree has it in that blocking mode. If these two links here, going from this switch to and this switch, are of equal cost, so let's say both of these are a gigabit link, if everything here is equal, it's then going to base this decision of designated and alternate based on who has the lowest port ID. So is this 1.0, port 1/0, and this one's port 2.0, and then this one might have a lower value than this one. So it'll decide based on the lowest value again. So the lowest port ID. Disabled is your final state, and that would be manually admin down. When a port is in this alternate backup mode and it's in this blocking status, if a link goes down for some reason, so say this goes down, well, let's say this one goes down, then this could come up. Spanning Tree will say, oh, things went bad, so this is now going to become a root port, so that we will go up this direction now. So if you're coming from switch at the bottom here, you could potentially go this way to get up to the root, or of course this way. And actually one of these, with this setup, one of these would be disabled as well, so potentially this one could be in alternate status. This could be a root. I believe technically it would be the opposite, since it'd be a lower cost, but that's the idea. So it would automatically switch over when it detects that we lost a link, and will bring up that connection. Once this link gets restored, then this link could go back into the alternate status. One issue you can run into with Spanning Tree is, unlike OSPF, it will automatically switch over to a new root if necessary. So similar to the failover idea with the links, if a switch comes in with a lower priority, it thinks that's a better switch to use. So you have to be cognizant of that when you insert it into a switch into your infrastructure that's existing. You could potentially switch over who has root privileges and cause some of this renegotiation to occur with your links if you put in a switch that has a very low MAC address, or a lower priority if you force the priority on a switch. So it's probably recommended that you set the priority value on your core switches, so that even if you insert another switch into your network, it won't take over as root, because it'll be based off the priority value first, and since you have priority value defined, then that would win. If you didn't do that and you just did it based off MAC, then you could potentially have an issue where you slap another switch in here, and then this one might have a lower MAC over this one. So then this becomes designated port, root port. This might become alternate. This would be designated, and it'll start renegotiating all these things so that traffic goes that way instead. So just be aware of that, and make sure you, and this is also something that Comes into play with VLAN trunking protocol as well. You want to make sure you don't put a switch in that has a higher revision number for VTP. Similar idea here. Make sure you are aware of the configuration of your switch before you place it into your network. Don't just hook it in there, as a blank slate and say everything's good. Be aware of your configuration before you start adding things to your network. So for spanning tree, there's a way to force the root bridge, as I mentioned, with the priority. So by default, the priority value, there we go, lowest priority. The default is 32,768. Most likely, you're going to want to set that as low as possible on your core switches. So you'd probably want to set that to 0. That way, you don't have to worry about it. That core switch is always going to be root no matter what. No one's going to get lower than 0. You can also have a different root bridge for each VLAN. So you can do an extended system ID, which allows for different root per VLAN. So that's also a way you could essentially balance out who has root privileges. Is if you had a half dozen core switches, one could be the root for each VLAN if you wanted to do it that way. So we'll clear this out. There's also a number of flavors of spanning tree, essentially. So flavors. Some of the flavors are, and I glossed over some of them in the beginning there. We have the original spanning tree. Does not support VLANs. It's not smart enough. It's relatively old. Slow response. It'll take anywhere from 30 to 50 seconds for it to realize that a link went down or some sort of failure occurred. This can also take care of switch failures as well, depending on how you design your network. If a whole switch goes down, as long as you have enough redundant links built in, you could potentially be okay, and spanning tree could take care of that. We also have PVST plus. This is Cisco proprietary, and you'll see some others of those as well. Cisco seems to always have a proprietary version of some sort of protocol out there that has additional features. The idea with this was that it adds VLANs. It also supports some fancier port features that we haven't gone over too much yet, which we will at some point in the near future, such as port fast, uplink fast, backbone fast, BPDU guard, which we'll talk about, BPDU filter or root guard, all sorts of things. It basically allowed for a bunch of additional features that you can assign your ports for security reasons and just efficiency reasons. There's also an IEEE standard of 802.1D-2004, which is kind of like the new standard essentially. It's an update of STP and includes 802.1W. There's an additional version which is probably the most common, and you're probably wondering, what is 802.1w? 802.1w is Rapid Spanning Tree Protocol, RSTP, which is also a standard. So RSTP was the original improved version of spanning tree, and then this 802.1d is an update to the update. So this is the newer version. This is probably the most common you'll see right now. So rapid spanning tree is an improvement of original spanning tree and provides, well, rapidity, faster convergence. It's overall faster. Replaced STP. It's the preferred protocol essentially, unless you're using the updated version. And it uses edge ports to designate ports that will never be connected to other switches, which you'll learn is the same as port fast, for example. So port fast is a Cisco version of edge ports. So what you do is you define, we'll draw it up here. If we have a switch and a switch and a switch, and these are connected, and then you have a couple access PCs connecting off the bottom of these switches. Each of these links would then be designated in RSTP as edge ports, or if you're using the Cisco commands, would be port fast. And what that does is it sends it puts these ports into forwarding mode immediately, which we'll talk about in a second. So what is forwarding mode? We'll talk about that in just a second. So this prevents the other modes that the ports have to go through and immediately starts forwarding traffic, so it's faster for those access devices that we know will never have a switch connected to it. So that is a slight concern though, because if you set it in edge mode or port fast mode and you connect a switch to it, then you may have a problem. So it's something to consider. There are ways to prevent issues though, even if you put it in port fast, such as these guard modes that we can use, which we'll talk about. So RSTP has this edge port mode. It makes things faster. It's the same idea as port fast. It immediately transitions to forwarding state, which we'll talk about. And there's other link types as well in RSTP. We have point-to-point. So it's a bit fancier. There's a lot more stuff in here. There's a point-to-point link mode, which is for direct connection to another switch. And then there's also a shared. So if you're on shared mode on a link, that would be like connecting to an older hub. So this is a full duplex. You're directly connected to another switch. Shared is as if you're connected to a hub, which is probably pretty rare nowadays, and runs on half duplex. Most likely you're going to have a mix of edge ports and point-to-point links. So let's blank this out. Well, we'll just erase. Should have made a new layer. Okay. So we have a couple other modes. We have Rapid PVST Plus. So you can guess this is a rapid version of the improved Cisco protocol. So this is Cisco proprietary. Adds VLAN. To RSTP. So this was an improvement over the original RSTP, and supports all those different port fast etc. commands, BPDU guard, root guard, loop guard, etc. and is the preferred Cisco protocol. So if you were running a mixed vendor environment, the preferred version would be RSTP or the updated version, the 802.1d. If you're running all Cisco, their recommendation is to run Rapid PVST Plus. And a lot of these, each version that keeps coming out, it tries to be faster and faster with the renegotiation of the links and failure takeovers. And then they add some additional features and such, but every version really tries to just come up with a better way of being faster with the convergence. We have one more version to mention, is Multiple Spanning Tree Protocol, so it's MSTP. MSTP is IEEE, so that's a standard, and it's based on a Cisco version called Cisco's MISTP. It's another version, another situation where a Cisco protocol got turned into a standard essentially. So it allows for multiple VLANs. In one instance, and supports a bunch of those port fast, etc. commands as well. And to really go over the very minute details between each of these different versions of spanning tree is not really a part of this. It's just to make you aware of the different versions that are out there and some of the basic ideas behind them. If you want to learn about the very specific details of timers and why one is different from the other, and having one VLAN instance in a spanning tree setup versus multiple VLAN instances in a spanning tree setup and things like that, that's something you can read into. We really just want to go over the basics of what spanning tree is, and then go ahead and do some basic configurations. So those are the different flavors that are out there. There's probably a few more as well. Most likely you'll be seeing RSTP and Rapid PVST out there in the wild, and you might start seeing some of that new 802.1d that's coming out. So each of these spanning tree flavors have a number of port states, and this is going back to the whole forwarding mode. So some of these port states are blocking, listening, learning. I suggest you also make good note of these and learn these. Forwarding, or disabled. So blocking is the first. This is essentially the order in which the ports go through during the spanning tree process. So they start out blocked. They'll then be transitioned into listening mode. So they listen for the path to root. They'll see who is out there, what's going on, and then as it listens, it will learn. So it'll start learning the MAC address of devices that are out there, so that it can start forwarding. It'll then start forwarding, and this is normal operation. They could also potentially be in admin down, so shutdown mode. So they'll go from blocking to listening for root. Once they find that out, they'll go into learning mode to learn the MAC addresses so they can start forwarding some frames, and then they'll go into forwarding mode, and then they'll start actually forwarding as expected. So blocking, listening, learning, forwarding. And each of these versions have go through those port statuses. Some ports will skip some of these though. So for example, our STP and PVST Plus and that, they have port fast and edge port mode. So instead of going through blocking, listening, learning, and taking 15 seconds per time, because there's a counter here where it takes a number of seconds between each, and the original version, I believe it was like 15 seconds or so between each status here. Depending on the version, those numbers will be different, but that's the basic idea behind it. And if you put it into edge mode or port fast mode immediately, then you don't have to wait such a long period of time for your host to get a connection so that they could then request DHCP. So the idea is you put it into edge mode or port fast mode so that it goes directly into forwarding mode, and then the second the host comes up and is able to request a DHCP address, the port is already ready to go, and there's no problem there. So it's really more of an issue when the whole network has to reboot or something like that, and all your switches have to come back on again, or the switch connected to a bunch of hosts reboots. You want that to be ready to go for the hosts so that you have less client-side issues. So from here we're going to do some spanning tree configuration. We'll do some bridge IDs and set port fast and BPDU guard and talk about why those things are important, and switch some modes between different spanning tree modes, and do some show commands.